video is on ionization energy. Ionization energy is energy needed to remove electrons. If you remember recently we talked about in class or in the videos oxidation states and charges. So that is related to this. Do some become positive and some become negative? Well, it's related to their ionization energy. So as the ionization energy increases, that means it's going to be harder, it's going to take more energy to remove electrons. So the higher the ionization energy, the less likely it is to lose electrons. The lower it is, the easier it is to remove them. So the trend is that within a group, so up and down in the columns, it increases as you go up. Within a period, though, it increases as you go to the right. So really this is the same trend as some of the other ones you'll see or have already seen. So it increases up and to the right. So as you go towards the noble gases, essentially, you're going to have higher ionization energy, so it's harder to remove electrons. So what this means is that metals have low ionization energy because they are to the left of the periodic table and more on the bottom. They're going to have lower ionization energy. It's going to be easier to remove electrons from them versus nonmetals, which are to the right and more up. They're going to have higher ionization energy. It takes more energy to remove electrons from them. So you can see in the graph here that you've got hydrogen and helium are your first two elements. Here's hydrogen, here's helium, and it gets, as you go to the right, it gets higher, the ionization energy. And then you've got your next row, so here's lithium, beryllium, and then magnesium. Now remember we said the trends aren't perfect. And part of this little dip here is related to where the electrons are and what we call shielding, which we're getting to. So you can see just overall, the ionization energy increases as you go to the right on a period. And you can see that like lithium to sodium right here, it kind of goes down. You can see this goes down, this goes down, this goes down, and so on. So here is a chart with ionization energies, and this is what we call the first ionization energy in this chart. First ionization energy is energy to remove just the first electron. There's also the second ionization energy. That would be energy to remove the second. Third ionization energy, third electron, and so on. So you can see just overall looking at the numbers that they tend to get bigger as you go towards the nonmetals and lower as you go towards the metals. So here's your separation between metals and nonmetals. And because the nonmetals over here are all higher ionization values, they're going to tend to be harder to remove electrons. That's why these typically have a negative charge. Your metals on the left side tend to have low ionization energies. It's easier. It takes less energy to remove the electrons, so they tend to be positive. It's easy to remove them. So, couple questions. Why does ionization energy increase as size decreases? Because it's the opposite trend. Atomic radius increases as you go towards francium, down and to the left. So ionization energy increases. It's harder to remove electrons as the atoms get smaller. Okay, so the reason is it has to do with that shielding. So if you have your nucleus where you have your positive charge, and let's compare, let's say, something like lithium. Okay, lithium has just two valence electrons, or sorry, just one valence electron. There you go, now you can see it. So we've got two electrons on the first energy level and that one on the outermost. So, okay, it's kind of spread out. As you go further across, though, let's talk about fluorine, for instance. Okay, fluorine, here's its nucleus. Now it has two electrons still in that first energy level, and it has 7 in the next. So you're thinking, okay, 7, maybe this is bigger, but fluorine's actually smaller because you have more positives, okay, more protons, and you have more negatives, more electrons. So they're actually being pulled in tighter. Okay? So as it gets tighter and smaller, it's harder to take those electrons away. Okay? So the second question, why does ionization energy increase as more electrons are removed? So as you lose an electron, okay, so let's say, for instance, lithium loses this electron. Okay? It's no longer there. Now it only has these two in there. Well, the positive charge hasn't changed. This is still the same amount. Well, now you've got these two electrons being pulled tighter in because they have the same amount of positive but less negative. So now it's going to take more energy to remove another electron. So here is a chart of ionization energies. And you can see over here we've got the equal IE1, first ionization energy, second, third, fourth, fifth, and so on. So on the top half you've got your first, period 1 and then period 2, and then below that you've got period 3. So if you look at lithium like we were just talking about, its first ionization energy is 520. That's the amount of energy it takes to remove the first electron. Look how much it increases as you try to remove it second. Because the electrons are being pulled in, and they call that shielding. Okay? Basically it's protecting them. There's that stronger attraction. So if you kind of just look at this, you can see ionization energies are increasing as you're going this way. They're also increasing as you're going, increases as you're going up, like sodium to lithium, magnesium to beryllium, aluminum to boron, and so on. And you can see as you go down, each progressive ionization energy, first, second, third, fourth, increases because it's more difficult to remove one. Alright, so quick practice. Sodium versus magnesium. So sodium is right here, magnesium's right here. Ionization energy increases as you go up and to the right. So magnesium would have a higher first ionization energy between those two. Comparing bromine and fluorine, increases as you go up, so fluorine would have the higher ionization energy. It takes more energy to remove electrons from fluorine than it does bromine.